Hello everyone. Today we will study how to find a closed form for nuclearizations, which is called solving nuclearizations. And we are looking for the simplest case, solving linear nuclearizations. First of all, let me introduce some terminology first. First one, homogeneous nuclearization. What's called homogeneous nuclearization? In a nuclearization, if every term contains the expression of AI, where AI is a term of a sequence. If every term contains the expression of AI, then we say the nuclearization is homogeneous. If every term contains in a nuclearization, if every term contains expression of AI, then we say the nuclearization is homogeneous. Let me show you some examples. Suppose we have a sub n equal to 2a sub n minus 1 plus 3a sub n minus 2. This is called homogeneous nuclearization because every term contains AI. Every term contains a term of a sequence AI. This is called homogeneous nuclearization. So this is homogeneous. Another example, if an equal to a sub n minus 1 plus 2n, then this is not homogeneous because the last term here, this term doesn't contain AI. This term doesn't contain AI. So this is not homogeneous. This is not homogeneous. Next, let me introduce what does linear nuclearization means. Linear nuclearization. What does linear means? Linear nuclearization. What does linear means? In a nuclearization, if each term contains only one factor of AI, if each term contains only one factor of AI, then we say the decolorization is linear. In a decolorization, if each term contains only one factor of AI, then we say the decolorization is linear. Let me show you some example. For example, a sub n equal to 2a sub n minus 1 plus 3a sub n minus 2. This is linear. Every term contains only one factor of AI. This is linear. Another example, if we have a sub n equal to a sub n minus 1 times a sub n minus 2. Then this is nonlinear. This is one term. This term contains two factors of AI. This is nonlinear. Another example, a sub n squared equal to twice a sub n minus 1 plus 3a sub n minus 2. This is nonlinear. First term has a sub n squared, which means a sub n times a sub n. This is nonlinear. First term contains two factors of AI. This is nonlinear. Next, let me introduce degree of a recurrent relation. What does degree means? Degree of a recurrent relation. In a recurrent relation, the difference of the highest and the lowest difference between the highest and the lowest index of AIs is called the degree of recurrent relation. In a recurrent relation, the difference of the highest and the lowest index of AIs is called the degree of a recurrent relation. For example, a sub n equal to twice a sub n minus 1. That's the highest index. That's the lowest index of AI. That's the highest index. That's the lowest index. The difference between the highest index and lowest index is 1. So this is called degree 1 recurrent relation. This is called degree 1 recurrent relation. In this example, the difference between the highest and the lowest degree is 2. This difference between the highest and the lowest index is 2. So we say for this nuclearization, the degree is 2. Another example, a sub n equal to 2a sub n minus 3. There's only 2 terms, but the difference between the highest and the lowest index is 3. So we say for this nuclearization, the degree is 3. This is a degree 3 nuclearization. Next, let's look at the simplest case first. Linear homogeneous nuclearizations. Linear homogeneous nuclearizations with constant coefficient. Linear homogeneous nuclearizations with constant coefficient. What does constant coefficient mean? For example, if we have an equal to 2a sub n minus 1 plus 3a sub n minus 2, that's called constant coefficient. Coefficient from the first term is 1. Coefficient from the second term is 2. Coefficient from the third term is 3. That's called constant coefficient. That's called constant coefficient. Then what does non-constant coefficient look like? Non-constant coefficient looks like this. 2n times a sub n minus 1. Here the coefficient is 2n. This is called a non-constant coefficient. This is called a non-constant coefficient. We only look, for this class, we only focus on the simplest case. Constant coefficient. Linear recurrence with constant coefficient. Let's look at the first example. First example. A sub n equal to a sub m minus 1 plus 12 a sub m minus 2. And this formula only works for n is greater than or equal to 2. So we must have 2 initial conditions. A0 equal to 3, A1 equal to 5. That's called initial condition. That's called the nuclearization. And that's called initial condition. Because for this formula, it only works for n greater than or equal to 2. The index cannot be negative. So for this formula, it only works for n greater than or equal to 2. And we must have two special cases. They are called initial conditions. Now, solve this equation. Solve this linear nuclearizations. First step. Let a sub n equal to x to the power n. First step, let a sub n equal to x to the power n. Then we have x to the power n. Let me rewrite everything first. Then a sub m minus 1 will be x to the power of m minus 1. A sub m minus 2 will be x to the power of m minus 2. Then, if I substitute, I have x to the power n equal to x to the power m minus 1 plus 12x raised to the power of m minus 2. If I substitute, a sub n is x raised to the power n. A sub m minus 1 is x raised to the power of m minus 1. A sub m minus 2 is x raised to the power of m minus 2. Then, if I simplify, I can divide every term by the lowest power of x. Divide every term by the lowest power of x. X raised to m minus 2, that's the lowest power. divide every term by the lowest power of x, I have s squared equal to x plus 12. If I divide every term by the lowest power of x, I have s squared equal to x plus 12. Then I can move everything to one side. It can be rewritten as s squared minus x minus 12 equal to 0. This equation has a name. It's called the characteristic equation. This equation has a name. It's called the characteristic equation of the nuclear relation. Characteristic equation of the nuclear relation. And this nuclear relation has degree 2 because the highest degree, the difference between the highest degree and the lowest degree is 2. This is called degree 2. This is called degree 2 nuclear relation. And we can see that for degree 2 nuclear relation, its characteristic equation also has degree 2. For degree 2 nuclear relation, its characteristic equation also has degree 2. Next, if we solve the equation, we have x minus 4, x plus 3 equal to 0. So s equal to 4, s equal to 3. That means the solution to the nuclear relation is, since s could be 4, we have 4 raised to power n. And the other solution is negative 3. We have 4 raised to power n and negative 3 raised to power n. We have two solutions. They are called linearly independent solutions. Linearly independent solution. They are called linearly independent solutions. We call the first solution S1, call the second solution S2. They are both solutions for A sub n. We call the first solution S1, call the second solution S2. So they are called linearly independent solutions. Now, for general solution, keep in mind. Note, for any linear homogeneous nuclear relation, of degree k, its general solution is always in the form of A sub n equal to C1 times S1, C2 times S2, CK times SK, where C1, C2, where the C's are real numbers, are constants, where C1, C2, CK are real numbers, and S1, S2, SK, they are K independent, linearly independent solutions. So keep this note in mind. For any linearly homogeneous nuclearization of degree k, its general solution is always in the form of an equal to C1 times S1, C2 times S2 plus Ck times Sk, where the C's are constants, are real numbers. S1, S2, Sk, they are linearly independent solutions. So here, in this example, we find two linearly independent equations. And the degree of this nuclearization is 2. So we know that the general solution of the equation has the form of the general solution to the nuclearization is an equal to C1 times S1, where S1 is 4 to the power n, plus C2 times S2, where S2 is negative 3 to the power n. That's the general solution, where C1, C2 are real numbers. That's the general solution. Next, we try to use the initial condition. To find C1, C2. That's the general solution. Next, we try to use the initial condition to find out what's C1, C2. So, use the initial condition to find C1, C2. A sub 0 is 3. That means for A sub 0, we plug in 0 for n, and the equation must equal to 3. If we plug in 0 for n, this equation must equal to 3. If I plug in 0 for n, C1 times 4 raised to power 0 plus C2 times negative 3 raised to power 0. This equation must equal to 3. Next, for next initial condition, A sub 1 is 5, means if I plug in 1 for each n, the equation must equal to 5. If I plug in 1 for n, the equation must equal to 5. Then we have two equations. If I simplify these two equations, if I simplify the first equation, 4 raised to power 0. 4 raised to power 0 is 1. I have C1. Negative 3 raised to power 0 is also 1. I have C1 plus C2 equal to 3. On the bottom, 4 raised to power 1 is 4. So first one is 4C1. Negative 3 raised to power 1 is negative 3. Negative 3 times C2 is negative 3C2 equal to 5. Here we have two equations with two unknowns. We can solve the equation for C1, C2. Here we have two equations for two unknowns. We can solve the equation for C1, C2. If I solve this equation, if I multiply first equation by 3, I can make 3C1 plus 3C2 equal to 9. If I keep the second equation the same, I have 4C1 minus 3C2 equal to 5. If I add them up, I have 7C1 equal to 14, which means C1 is 2. If C1 is 2, I plug in 2 for C1 and solve for C2. So 2 plus, if I substitute 2 for C1, I have 2 plus C2 equal to 3. So C2 equal to 1. So here we find that use initial condition, we find out that C1 is 2, C2 is 1. So the final answer, let me put it here. The general solution, it was A sub n equal to C1 times 4 to the power n plus C2 times negative 3 raised to power n. If we plug in the value for C1, C2, the final answer is A sub n equal to C1 is 2, 2 times 4 to the power n. C2 is 1, plus 1 times negative 3 to the power n. That's the final answer. That's the general solution. That's the general solution to the linear recurrent relation. That's the final answer. That's the general solution to this recurrent relation. Let's look at a different example. Find the general solution to the recurrent relation Find the general solution to the recurrent relation A sub n equal to 3A sub n minus 1 plus 10 times A sub n minus 2, where with two initial conditions that says A1 equal to 16, A2 equal to 38. So this recurrent relation doesn't start from A0, it starts from A1, A2. They give you A1, A2 as initial condition. So same thing. First step, find a characteristic equation first. So first step, let an equal to x raised to power n. Let an equal to s raised to power n. Find a characteristic equation first. Then a sub m minus 1 equal to x raised to m minus 1. A sub m minus 2 equal to x raised to m minus 2. Find the characteristic equation first. If I substitute, I have x raised to power n equal to 3 times x raised to power of m minus 1 plus 10 times x raised to power of m minus 2. Then divide each term by the lowest power of x. Divide each term by the lowest power of x. Here I divide by x raised to m minus 2. So the characteristic equation is s squared equal to 3x plus 10. The characteristic equation is x squared equal to 3x plus 10. Next, we try to solve this equation for x. Solve this equation for x. This is called a characteristic equation. That's the characteristic equation. If I solve the equation, I have x minus 5, x plus 2 equal to 0, x equal to 5, and s equal to negative 2. Then if I substitute 5 and 2 into an here, if I substitute 5 and 2 into an, I get two independent solutions. S1 equal to 5 raised to power n. S2 equal to negative 2 raised to power n. They are called independent solutions, linearly independent solutions. They are called linearly independent solutions. The general solution is A sub n. This recurrent relation has degree 2. This recurrent relation has degree 2. So the general solution should be C1 times S1 plus C2 times S2. That's the general solution. Next, we need to find C1, C2. Find C1, C2 using the initial condition. We need to find C1, C2 by using the initial condition. If I substitute 1 for n, I have 5 to the power 1 is 5. That's 5C1. If I substitute 1 for n, I have C2 times negative 2, which is negative 2C2. And we know A1, A sub 1 equal to 16. If I substitute 1 for each n, this equation equal to 16. For A sub 2, I plug in 2 for n. If I substitute 2 for n, I have 5 to the power 2 is 25. I have 25 times C1. If I substitute 2 for n, I have negative 2 to the power 2 is 4. I have 4C2. And this equation equal to 38. A sub 2 is 38. Then if I simplify both equations, here what I can do is I can multiply first equation by 2. If I multiply first equation by 2, I have 10C1 minus 4C2 equal to 32. And I leave the second equation the same. I have 25C1 plus 4C2 equal to 38. If I add the equation together, I have 35C1 equal to 70. So C1 is 2. Once I know C1, I can plug in C1 to one of the equations, solve for C2. So I have, let me plug in here, 5 times 2 minus 2 times C1 minus 2 times C2 equal to 16. Solve an equation for C2. That's 10. Subtract 10 from both sides. I get negative 2C2 equal to 6. So C2 equal to negative 3. Once I know C1 and C2, I can substitute here. So the general solution is A sub n equal to 2 times 5 to the power n minus 3 times negative 2 to the power n. This is the general solution. This is the general solution to the equation, to the recurrent relation. This is the general solution to the recurrent relation. Next equation. Find the general solution to the recurrent relation A sub n equal to 6 times A sub n minus 1 minus 9 times A sub n minus 2 with initial conditions that A1 equal to 3, A2 equal to 0. So, same procedure. Let's find the characteristic equation first. Let an equal to x to the power n. Then A sub n minus 1 is x raised to n minus 1. And A sub n minus 2 is x raised to n minus 2. If we substitute, we have x raised to power n equal to 6x raised to power of n minus 1 minus 9 times x raised to n minus 2. Then divide every term by the lowest power. We have x squared equal to 6x minus 9. Then move everything to one side. S squared minus 6x plus 9 equal to 0. This equation can be factored as x minus 3 times x minus 3 equal to 0, which means x minus 3 squared equal to 0. So this equation has only one solution, s equal to 3. So the linear independent solution is S1 equal to, if I plug in 3 here, S1 is 3 raised to power n. The linearly independent solution is S1 equal to 3 raised to power n. Then this is a degree 2 denuclearization. The general solution must have the form AN equal to C1 times S1 plus C2 times S2. This is a degree 2. This is a degree 2 denuclearization. The general solution must have the form of AN equal to C1 times S1 plus C2 times S2. But there's only one solution. What can we do here? There's only one solution. What can we do? Now, be very, very careful here. This solution has multiplicity 2. This solution has multiplicity 2. These two solutions has the same value. This solution has multiplicity 2. Now there's one more rule here. There's one more rule, keep it in mind. Note. Note. For any solution of the characteristic equation, with multiplicity k, for any solution of the characteristic equation with multiplicity k, the expressions x to the power n, n x to the power n, n squared x to the power n, until n raised to k minus 1 x to the power n. This expression, they are k independent solution to the denuclearization. They are k linearly independent solutions to the homogeneous, to the linear homogeneous denuclearization. So keep this rule in mind. For any solution of the characteristic equation with multiplicity k, the following expressions: x to the power n, n times x to the power n, n squared x to the power n, n raised to k minus 1 x to the power n. They are k linearly independent solutions to the linear homogeneous denuclearization. So here, 3 is a solution to the characteristic equation with multiplicity 2. So it should be, the S2 should be n times 3 to the power n. Power 2 minus 1 is power 1 here. Power 2 minus 1 is power 1. Here multiplicity is 2. 2 minus 1 is 1. So it's n times 3 to the power n. That's another linear independent solution. So the general solution. Now here we have two linear independent solutions. The general solution can be rewritten as A sub n, an equal to C1 times S1, C2 times S2, n times 3 to the power n. That's the general solution. Next, we need to use the initial condition. We need to use an initial condition to find C1 and C2. The general solution is an times C1, an equal to C1 times 3 to the power n plus C2 times n times 3 to the power n. First initial condition says a sub 1 equals 3. If I substitute 1 for n, I must get 3. The equation must equal to 3. We have C1 times 3 plus, if I substitute 1 here, I have 3 times C2 equal to 3. So if I substitute 1 for each n, the equation equal to 3. If I substitute 2 for each n, the equation equal to 0. If I substitute 2 for each n, the equation equal to 0. So 3 squared is 9. I get 9C1 here. If I substitute 2 for each n, 3 squared is 9. 9 times 2 is 18. So 9 times C1 plus 18 times C2 equal to 0. Then solve the equations for C1 and C2. If I divide the second equation by 9, I can make C1 plus 2C2 equal to 0. If I divide the first equation by 3, I can make C1 plus C2 equal to 1. Then, if I use the second equation, subtract by the first equation. C1 minus C1 can cancel. 2C2 minus C2 is C2. 0 minus 1 is negative 1. So I can find that C2 is negative 1. Once I know C2, I can plug in C2 here. Plugging C2 to this equation, I can solve for C1. So C1 plus negative 1 plus 1 equal to 1. C1 plus negative 1 equal to 1. If I add 1 to both sides, C1 equal to 2. So we know that C1 is 2, C2 is negative 1. So the general solution, an is 2 times 3 to the power n. C2 is negative 1, so we have negative n times 3 to the power n. That's the general solution. To this recurrence relation. So, for any solution to the characteristic equation with multiplicity other than 1, we must find multiple solutions from here. If multiplicity of 3 is 2, we need to find 2 solutions for this answer. If the multiplicity for 3 is 2, we need to find 2 solutions for this answer. If multiplicity is 3, we need to find 3 solutions for this answer. So first one is 3 raised to power n. Second solution can be generated using n times 3 to the power n. If the multiplicity is 3, next solution will be n squared times 3 to the power n. So if the multiplicity is k, for any solution to the characteristic equation, if the multiplicity is k, we must find k independent solution using these formulas. If the multiplicity of any solution is k, we need to find k linearly independent solution using this formula. Next, let's look at a simpler equation. Find a general solution to the recurrence relation an equal to 4 times a sub n minus 1 with initial condition a0 equal to 3. So same procedure. First of all, let an equal to x raised to power n. Then a sub n minus 1 can be rewritten as x to the power of n minus 1. Then plug in, find a characteristic equation. Plug in. we have x to the power n equal to 4 times x raised to n minus 1. Then divide both sides by the lowest power of x. Divide both sides by the lowest power of x. We have s equal to 4. This is the characteristic equation. It's also the solution of the equation. This is the characteristic equation. If we plug in 4 for x, we have s1 equal to 4 to the power n. That's the linearly independent solutions. Since this declaration has degree 1, this difference between the highest and lowest index is 1. This declaration has degree 1. So the general solution has the form of an equal to c1 times s1. Since this linear declaration has degree 1, the general solution has the form of an equal to c1 times s1. And s1 is 4 raised to power n. Then we use the initial condition to find c1. If I substitute 0 for n, a sub 0 equal to c1 times 4 to the power 0. If I substitute 0 for n, this equation equal to 3. Then solve the equation for c1. We know that 4 to the power 0 is 1, so c1 equal to 3. For the final answer, plug in c1. an equal to 3 times 4 to the power n. That's the general equation. It's the general equation to the declaration here. This linear declaration has only degree 1. It's much easier than degree 2. Declaration. Next, let me show you a different type of problems. Linear non-homogeneous declarations. Linear non-homogeneous declaration with constant coefficients. Linear non-homogeneous declaration with constant coefficients. It looks like this. For example, an equal to 4 times a sub n minus 1 minus 9n. This term doesn't contain a sub I. This term doesn't contain the sequence a sub I. So this is a non-homogeneous. Declaration. In this equation here, this part is called the non-recursive part. This part is called the non-recursive part of the declaration. This part is called the non-recursive part of the declaration. This is called the non-recursive part of the declaration. In this problem, the initial condition is a sub 0 equal to 3. For this problem, the initial condition is a sub 0 equal to 3. And for this declaration here, negative 9n is called the non-recursive part. It's called the non-recursive part of the declaration. So in this situation, for non-homogeneous declaration, keep this in mind. In this situation, for non-homogeneous declaration, keep this in mind. The general solution to the non-homogeneous nuclearization. The general solution to a non-homogeneous nuclearization always has the form of AN equal to AMP plus ANH, where AMP is called a particular solution and ANH is called a homogeneous solution. Of the denuclearization. Keep this in mind. The general solution to a non-homogeneous denuclearization always has a form of AN equal to AMP plus ANH, where AMP is called a particular solution and ANH is called a homogeneous solution of denuclearization. Keep this in mind. Next, let me explain to you what does particular solution and homogeneous solution means. Next, let me explain to you what does particular solution and homogeneous solution means. Particular solution. A solution that satisfies the solution that satisfies the non-homogeneous denuclearization is called a particular solution. It's called a particular solution to the denuclearization. Denoted by A sub n p. A solution that satisfies the non-homogeneous denuclearization is called a particular solution to the denuclearization, denoted by A sub n of p, A sub n p. So any solution that satisfies this denuclearization is called a particular solution. Next, let me explain what does homogeneous solution means. The denuclearization is AN equal to 4 times A sub n minus 1 minus 9n. Net minus 9n here is called the non-recursive part. Note, keep one thing in mind. In a non-homogeneous recurrent relation, if we remove the non-recursive part, what's left? The resulting equation is called the associated homogeneous recurrent relation. In a non-homogeneous recurrent relation, if we remove the non-recursive part, what's left? The resulting equation is called the associated homogeneous. It's called associated homogeneous recurrent relation. So this part is called associated homogeneous recurrent relation. This part is called a non-recursive part. If we remove the non-recursive part, what's left is called associated homogeneous recurrent relation. A homogeneous solution The homogeneous solution is the solution to this associated homogeneous recurrent relation. A homogeneous solution is a solution to this part, to this recurrent relation here. So, the general solution to the associated homogeneous recurrent relation is called the homogeneous solution. Denoted by A sub NH. In this example, In this example, the homogeneous solution A sub nh, the homogeneous solution is the general solution to the associated homogeneous nuclearization to An equal to 4 times Am minus 1. So in this example, the homogeneous solution ANH is the general solution to the associated homogeneous nuclearization An equal to 4 times Am minus 1. And we know that the general solution to this nuclearization is A0 equal to C1 times 4 to the power of n. A0 equal to C1 times 4 to the power of n. So the homogeneous solution to this nuclearization is C1 times 4 to the power n, which is the general solution to this nuclearization. That's called a homogeneous solution to this nuclearization. And for the previous example, let me correct one thing. This is called general solution. The one before we plug in initial condition is called general solution. The answer after we plug in initial condition, after we find C1, answer after we plug in initial condition, this is called a solution to this nuclearization. This is not general solution. This is the general solution. This is called a solution to this equation, to this nuclearization. And same thing for the previous example. The one before we plug in initial condition, before we solve for C1, C2, that's called general solution. The one after we plug in C1, C2, this answer is called the solution. And same thing. The one before we plug in C1, the one before we plug in initial condition, before we solve for C1, C2, this is called general solution. And after we solve for C1, C2, this is called a solution, not general solution. This is called a solution. This is called a solution to this nuclearization. The general solution is the one before we solve for C1, C2. And same thing for the first example. The one before we solve for C1, C2, this is general solution. After we plug in C1, C2, this is called the solution, not general solution. This is called a solution. This is not general solution. This is called a solution to the nuclearization. So make this correction. Next, let me show you how to find particular solutions. In general, finding particular solution is very, very hard. So let me first of all show you some special form for particular solutions. A sub np. Let me show you some special form for particular solutions. Case 1. If the non-recursive part is a polynomial of degree k, then if the non-recursive part is a polynomial of degree k, then the particular solution an of p, a sub np, must be a general polynomial of degree k. If the non-recursive part is a polynomial of degree k, then the particular solution must be a general polynomial of degree k. What does general polynomial of degree k means? What does general polynomial of degree k means? General polynomial of degree k when the general polynomial of degree 1 looks like this: ax plus b general polynomial of degree 2 looks like this: ax squared plus bx plus c. General polynomial of degree 3 has the form of as cubed plus bx squared plus cx plus d, and so on. In a special case, general polynomial of degree 0. General polynomial of degree 0 is a constant. Could be any letter, could be any constant. So those are general polynomials. Degree 0, degree 1, degree 3, degree 2, degree 3, and so on. Those are called general polynomials. So if the non-recursive part is a polynomial of degree k, then the particular solution must be the general polynomial of degree k. Case 2. If the non-recursive part has the form, if the non-recursive part is in the form of if the non-recursive part is in the form of a polynomial of degree k times r to the power n. If the non-recursive part is in the form of a polynomial of degree k times n to the power r, where r is not a solution, where r is not a solution of the characteristic equation, then the particular solution must have the form of ANP equal to a general polynomial of degree k times r to the power n. If the non-recursive part is in the form of polynomial of degree k times r to the power n, where r is not a solution of the characteristic equation, then the particular solution must have the form the general polynomial of degree k times r to the power n. That's case 2. Case 3, if the non-recursive part has the same form as case 2. If the non-recursive part has the same form in case 2, if the non-recursive part has the form of polynomial of degree k times r to the power n, polynomial of degree k times r to the power n, where r is a solution. In case 2, r is not a solution of the characteristic equation. Case 3, r is a solution. Of the characteristic equation. Then the particular equation the particular solution must have the form of AMP, the particular solution. It must have the form of general polynomial of degree k general polynomial of degree k times r to the power n times one more thing times n to the power m times n to the power m, where m is the multiplicity of r. If r is a solution of a characteristic solution, r will have a multiplicity. For example, if the characteristic equation has the form of x minus r to the power 1 equal to 0, the x equal to r, multiplicity of r is 1. If the characteristic equation contains the factor x minus r to the power 2 equal to 0, s equal to r, then this r has multiplicity of 2. If the characteristic equation has the form of s minus r to the power 3 equal to 0, solve the equation s equal to r, then the multiplicity of r is 3. That's how we find multiplicity. So this particular solution has the form that general polynomial of degree k times r to the power n times, there's one more term here, there's one more factor here, times n to the power m, where m is the multiplicity of r. M is the multiplicity of r. This n is the same as this n. This n is the same as this n. M is the multiplicity of r. So keep these three cases in mind. For this class, we only deal with these three simplest cases. In this class, we only deal with these three simplest cases. Keep these three cases in mind. Those are the special form for the particular solutions. Keep it in mind. Now let's go back to this example here. a sub n equal to 4 times a sub n minus 1 minus 9n. First step, when we solve for recurrent relation, first step, find the homogeneous solution. So for this example, we know that the homogeneous solution we just found, that's C1 times 4 to the power n. This is homogeneous solution. Solve the associated homogeneous recurrent relation. Solve this recurrent relation first. We get the general solution, C1 times 4 to the power n. We get a general solution, C1 times 4 to the power n. Next, we try to find the particular solution. Here, the non-homogeneous part here, the non-recursive part. The non-recursive part here is a polynomial of degree 1. The non-recursive part is a polynomial of degree 1. So the particular solution, it must have the form of general polynomial of degree 1. It must be an plus b. This is a polynomial of degree 1. So the particular solution must be the general polynomial of degree 1. That's case 1. Since the non-recursive part is a polynomial, this is a polynomial of degree 1. So the particular solution must have the form of general polynomial of degree 1, which is an plus b. The variable here is n. So this is the general. So the particular solution must have the form of an plus b. Next, we try to solve for a and b. How do we solve for a and b? We try to plug in the particular solution into the original recurrent relation. Solve for a and b. So a sub n is an plus b. Then a sub n minus 1 will be a times n minus 1 plus b. We plug in n minus 1 for n. Then plug in an and an minus 1. Particular solution is a solution to this recurrent relation, so we are allowed to plug in. Particular solution is a solution to this recurrent relation, so we are allowed to plug in a sub n here. If we plug in, we have an plus b, that's on the left side, equal to 4 times a times a n minus 1 plus b minus 9n. Then try to solve the equation for a and b. Try to match the coefficients, solve for a and b. In general, leave the left side the same. Don't touch the left side. Simply for the right side. It's very similar as we solving partial fractions. If you remember partial fraction from your calculus class. So I first of all distribute 4. I get 4a n minus 1 plus 4b minus 9n. Distribute 4a, I get 4an minus 4a plus 4b minus 9n. Then group the term with n together. I have 4a minus 9n plus negative 4a plus 4b. That equal to an plus b. Then if two polynomials equal to each other, the coefficient of each term must be the same. So by matching the coefficient, we can see that a equal to 4a minus 9. b equal to negative 4a plus 4b. b equal to negative 4a plus 4b. Then solve these two equations for two variables. If we solve the first equation, I have negative 3a equal to negative 9. So a equal to 3. Once I know a, I can plug in a to find b. 3 times negative 4 is negative 12 plus 4b. Move 4b over. I have negative 3b equal to negative 12. Then we divide both sides by negative 3. B equal to 4. Now we know a, we know b. So we know particular solution. The particular solution is 3n plus 4. That's the particular solution. So this is homogeneous solution. This is particular solution. The general solution to this equation, to this recurrence relation, the general solution is the homogeneous solution. The general solution is the homogeneous solution plus the particular solution. The general solution has a form that homogeneous solution plus the particular solution. So general solution has the form of C1 times 4 to the power n plus 3m plus 4. That's the general solution. Now if we try to find a solution, we need to use the initial condition. To find C1. So in this problem, the initial condition is A0 equal to 3. So using the initial condition, find C1. We have an equal to C1 times 4 to the power n plus 3m plus 4. And we know that the initial condition A0 equal to 3. Which means if I plug in 0 for each n, this equation will equal to 3. So I get C1 times 4 to the power 0 plus 3 times 0 plus 4 equal to 3. Then solve the equation for C1. 4 to the power 0 is 1. I get C1 by itself. 3 times 0 is 0. Number 4 stays the same. Then solve for C1. C1 equal to negative 1. So the general solution, I plug in negative 1 for C1. So I have negative 1 times 4 to the power n plus 3m plus 4. This is the solution to the recurrence relation. And this is called general solution. This is a solution to the recurrence relation. The one before we solve for C1. The expression before we solve for C1 is called general solution. The expression after we solve for C1 is called the solution to the recurrence relation. Next example. Find a solution to the recurrence relation. A sub n equal to 5a sub n minus 1 minus 6a sub n minus 2 plus 2 times n squared with initial conditions a0 equal to 0, a1 equal to negative 17. So first of all, this is a non-homogeneous recurrence relation. This is non-homogeneous. This term doesn't contain ai. This term doesn't contain a sub I. This is a non-homogeneous recurrence relation. So first step, we find a homogeneous solution first. So remove the non-recursive part. we temporarily remove the non-recursive part. The associated recurrent relation, associated homogeneous recurrent relation is an equal to 5a sub n minus 1 minus 6a sub n minus 2. We temporarily remove the non-recursive part. It's called associated homogeneous recurrent relation. Find the homogeneous solution first. So let an equal to x raised to power n. Then a sub n minus 1 is x raised to n minus 1. A sub n minus 2 is x raised to n minus 2. If we substitute, we have x to the power n equal to 5x to the power n minus 1 minus 6x raised to n minus 2. Divide by the lowest power. Divide every term by the lowest power. The characteristic equation is s squared equal to 5x minus 6. Move everything over. S squared minus 5x plus 6. If we solve the equation for characteristic equation, we have x minus 2, x minus 3. Solve the equation, s equal to 2, s equal to 3. So the linearly independent solution to the homogeneous for this homogeneous recurrent relation is C1 times C1 times 2 to the power n. Plug in 2 here. C1 times 2 to the power n plus C2 times 3 to the power n. So the linear independent solution is these two solutions here. S1 equal to 2 to the power n, plug in 2 here. S2 equal to 3 to the power n. The general solution to the homogeneous recurrent relation is C1 times 2 to the power n plus C2 times 3 to the power n. That's the general solution. So the general solution of an associated homogeneous recurrent relation is called homogeneous solution. This is A sub n of h. This is A sub n of h. That's C1 2 to the power n plus C2 times 3 to the power n. That's the homogeneous solution. Next, we try to find the particular solution. Look at the non-recursive part. The non-recursive part it's a polynomial of degree 2. The non-recursive part is a polynomial of degree 2. The non-recursive part is polynomial of degree 2. So the particular solution must have the form. It must be a general polynomial of degree 2. It must be the general polynomial of degree 2. General polynomial is an squared plus bn plus c. Here variable is n. This is a general polynomial of degree 2. This is a general polynomial of degree 2. Next, we try to plug in a particular solution into an original recurrent relation. Solve for A, B, and C. Solve for A, B, and C. Plugging a particular solution to this recurrentization here. Solve for A, B, and C. So in this equation, we need to use A sub n minus 1 and A sub n minus 2. Let me find it first. So A and P. The particular solution is an squared plus bn plus c. A sub n minus 1 A sub n minus 1 will be A times n minus 1 squared plus B times n minus 1 plus C. A sub n minus 2 equal to A times n minus 2 squared plus B times n minus 2 plus C. Then we plug in these three terms into the original recurrentization. Let me write a formula here. AN equal to 5 times A sub n minus 1 minus 6 times A sub n minus 2 plus 2 to the power n squared. 2 times n squared. Then plugging left side is an squared plus bn plus c. That's left side. Right side here is 5 times A sub n minus 1, this equation. A times n minus 1 squared plus B times n minus 1 plus C minus 6 times A sub n minus 2, this entire equation here. A times n minus 2 squared plus B times n minus 2 plus C plus 2n squared. Then try to simplify right side. Match the coefficient. Simplify right side and match the coefficient. So on the left side, I first of all distribute phi. I have phi A expand the perfect square. That's n squared minus 2n plus 1. Distribute phi. I get phi B times n minus 1. Distribute phi here. I get phi C. Distribute 6. I get 6a times n squared minus 4n plus 4. Distribute 6. I get 6b times n minus 2. Sorry, it should be minus 6c. Minus 6b here. Minus 6b. Minus 6c. Plus 2n squared. Last term is plus 2n squared. Then if we multiply out, we have phi a n squared minus 10an 10a times n plus phi a plus phi b times n minus phi b plus 5c minus 6an squared plus 24an minus 24a minus 6bn plus 12 plus 12b minus 6c plus 2n squared. Then try to put n squared together. Put the coefficient of n squared together. We have 5a, 6a, 5a, 6a, and plus 2. Next, put the coefficient of n together. I have negative 10a plus 5b plus 24a minus 6b next put a constant together. We have 5a minus 5b plus 5c minus 24a plus 12b minus 6c. Those are the constant term. Then try to match the coefficient an squared plus bn plus 3. So if I try to match the coefficient, a equal to 5a minus 6a plus 2, b equal to negative 10a plus 5b plus 24a minus 6b, c equal to 5a minus 5b plus 5c minus 24a plus 12b minus 6c. If I simplify the first equation, I have negative a here plus 8. I have 2a equal to 2, which means a equal to 1. If I simplify the second equation, I have 5b minus 6b. 5b minus 6b is negative b. Add b to both sides. I have 2b. Negative 10a plus 24a is 14a. And we know that a is 1. So 2b equal to 14. Then divide both sides by 2. b equal to 7. If we simplify the third equation, 5c minus 6c is negative c. Add c to both sides. 2c equal to, here we have 5a minus 24a is negative 19a. Negative 5b plus 12b. Negative 5b plus 12b is 7b. And we know that a is 1, b is 7. 7 times 7 is 49. So 2c equal to 30. C equal to 15. So we find A, B, C. A is 1, B is 7, C is 15. So the particular solution is 1n squared plus 7n plus 15. That's the particular solution. And that's the homogeneous solution. The general solution AN is always homogeneous solution plus particular solution. Homogeneous solution plus particular solution, which is C1 times 2 to the power n plus C2 times 3 to the power n plus the particular solution n squared plus 7n plus 15. Next, we need to use the initial condition. Find C1 and C2. Using the initial condition, find C1 and C2. So we have A0 equal to 0, A1 equal to -17. The general solution is AN equal to C1 times 2 to the power n plus C2 times 3 to the power n plus the particular solution n squared plus 7n plus 15. Then for A sub 0, I plug in 0 for A. Plug in 0 for n. If I plug in 0 for n, this equation must equal to 0. So if I plug in 0 for n, 2 to the power 0, 2 to the power 0 is 1. So I get C1 here. 3 to the power 0 is also 1. I get C2 here. 0 squared is 0. 7 times 0 is 0. Plus 15, that equal to 0. If I plug in 0 to the equation, I get 0. If I plug in 1 for n, this equation will equal to -17. So for A sub 1, I plug in 1 for n. This equation will equal to -17. If I plug in 1, 2 to the power 1 is 2, so I get 2C1. 3 to the power 1 is 3, so I get 3C2. 1 squared is 1. Plus 7 plus 15. 1 plus 7 is 8. 8 plus 15 is 23. That equal to -17. Then solve these two equations. Solve these two equations for C1, C2. Solve these two equations for C1, C2. If I simplify first equation, I have C1 plus C2 equal to -15. If I simplify the second equation, 2C1 plus 3C2 equal to -40. Then in the first equation, if I multiply first equation by -2, I have -2C1 minus 2C2 equal to 30. And I leave the second equation the same. 2C1 plus 3C2 equal to -40. If I add the equation together, C2 equal to C1 can cancel. I have 1C2 equal to -10. Once I know C2, I can plug in C2, find C1. So here C1 plus -10 equal to -15, which means C1 equal to -5. So that's C1, C2. For the final answer, plug in C1, C2. That's the solution to the Denuclearization. AN equal to -5 times 2 to the power n minus 10 times 3 to the power n plus n squared plus 7n plus 15. That's the solution. That's the solution to the Denuclearization. This is called general solution. This is not a solution. This is called general solution. The expression before we plug in C1, C2 is called the general solution. This is called the solution of the Denuclearization. Next example. Find a solution to the Denuclearization. A sub n equal to 5a sub n minus 1 minus 6a sub n minus 2 plus 6 to the power n with initial conditions a0 equal to 0, a sub 1 equal to 10. So this is a non-homogeneous Denuclearization. This is a non-homogeneous Denuclearization. This term here doesn't contain a sub I. This term here doesn't contain a sub I. This is called non-homogeneous Denuclearization. So we need to find the homogeneous solution first. We need to find a homogeneous solution first, because the general solution is always homogeneous solution plus particular solution. So find homogeneous solution first. So find a homogeneous solution first. If we observe the associated homogeneous nuclearization, this is exactly the same as the previous problem. If we look at the associated homogeneous nuclearization, if we remove the non-recursive part, the associated homogeneous nuclearization, this looks exactly the same as the previous problem. So we can use the homogeneous solution from the previous problem. We can use the homogeneous problem from the previous problem. Since the associated homogeneous nuclearization looks exactly the same as the previous problem, the homogeneous solution must be the same. C1 times 2 to the power n plus C2 times 3 to the power n. Next, for the particular solution, observe the non-recursive part. Here, the non-recursive part. The non-recursive part is 6 to the power n. That can be rewritten as 1 times 6 to the power n, which is number 1. We can consider number 1 as a degree 0 polynomial. We can consider number 1 as a degree 0 polynomial. So that's in case 2. That's case 2, the special form of particular solution. That's case 2. The non-recursive part is the polynomial of degree k times r to the power n, and r is not a solution of the characteristic equation. Here, 6 is not a solution to the characteristic equation. The solution to the characteristic equation is 2 and 3. Number 6 is not a solution of the characteristic equation, so that's in case 2. The non-recursive part is degree 0 polynomial times 6 to the power n. Then the particular solution must be a general degree 0 polynomial. A general degree 0 polynomial times 6 to the power n. A general degree 0 polynomial, constant a is a general degree 0 polynomial times 6 to the power n. Then we try to plug in the particular solution, solve for a. Plug in the particular solution, solve for a. If I plug in, what do I get? Let me find a. Let me find a sub n minus 1 first. A sub n minus 1 is a times 6 to the power of n minus 1. A sub n minus 2 will be a times 6 to the power of n minus 2. If we plug in here, what do we get? On the left side, we have a times 6 to the power n. First term on the right side, first term is 5 times a times 6 to the power of n minus 1. Second term is 6 times a times 6 to the power of n minus 2 plus 6 to the power n. So here, every term contains 6 to some power. So first of all, divide by the lowest power of 6. Divide by the lowest power of number 6. Lowest power is 6 to the n minus 2. Then on the left side, we have a times 6 squared. On the right side, if I cancel 6 here, there's a 6 left on the top. 6 times 4 is 30. I get 38. 6 to the power n minus 2 cancel completely. I get 6a in the second term. In the third term, I have 6 squared left. So left side can be rewritten as 36a. Right side, if I combine like term, I get 24a. 6 squared is 36. And then subtract 24a from both sides. I get 12a equal to 36. Divide both sides by 12. A equal to 3. Divide both sides by 12. A equal to 3. So the particular solution. A and P is 3 times 6 to the power n. 3 times 6 to the power n. That's the particular solution. And the general solution AN is the homogeneous solution plus the particular solution. Homogeneous solution, the same as the previous problem, is C1 times 2 to the power n plus C2 times 3 to the power n plus the particular solution 3 times 6 to the power n. Then to find a solution, we use the initial condition here, solve for C1, C2. Use the initial condition here, solve for C1, C2. Initial condition says A0 equal to 0, A1 equal to 10. The general solution is AN equal to C1 times 2 to the power n plus C2 times 3 to the power n plus 3 times 6 to the power n. Then I plug in 0 for A sub 0. I plug in 0 for each n. This equation must equal to 0. If I plug in 0 for n, 2 to the power 0 is 1. 1 times C1 is C1. If I plug in 0 for n, 3 to the power 0 is 1. 1 times C2 is C2. If I plug in 0 for n, 6 to the power 0 is 1. 3 times 1 is 3. And A sub 0 equal to 0. First equation equal to 0. Next, for A sub 1, I plug in 1 for each n. 2 to the power 1 is 2. 2 times C1 is 2C1. 3 to the power 1 is 3. 3 times C2 is 3C2. If I substitute 1 here, 6 to the power 1 is 6. 3 times 6 is 18. That equal to 10. Then if I simplify the first equation, that's C1 plus C2 equal to negative 3. If I simplify the second equation, I have 2C1 plus 3C2 equal to negative A. Then I can multiply first equation by negative 2. If I multiply first equation by negative 2, I have negative 2C1 minus 2C2 equal to 6. Second equation is 2C1 plus 3C2 equal to negative A. Then if I add the equation together, I have C2 equal to negative 2. Then once I know C2, I can substitute C2 here, find C1. C1 plus negative 2 equal to negative 3. Add 2 to both sides. C1 equal to negative 1. So the solution to the equation is negative 1, plug in here, plug in C1, C2 here. Plug in negative 1, plug in C1, C2 into the general solution. Negative 1 times 2 to the power n minus 2 times 3 to the power n plus 3 times 6 to the power n. This is a solution to decolorization. This is a solution to the decolorization. This is the general solution. This is the general solution. This is the solution to the decolorization. Next example, find the solution to the decolorization. A sub n equal to 5a sub n minus 1 minus 6a sub n minus 2 plus 3 to the power n with initial conditions a0 equal to negative 1, a1 equal to 3. So this is a non-homogeneous decolorization. We can see the last term here doesn't have a sub I. This is a non-homogeneous decolorization. And first of all, in order to find a solution, we need to first of all find the homogeneous solution. And we can see that if I remove the non-recursive part, the associated homogeneous nuclear relation is the same as the previous problem. The associated homogeneous nuclear relation, this part, is the same as the previous problem. So the homogeneous solution must be the same. So the homogeneous solution must be the same, which is C1 times 2 to the power n plus C2 times 3 to the power n. Next, we try to find a particular solution. Particular solution depends on the non-recursive part. Here, the non-recursive part is 3 to the power n. That can be rewritten as, we can consider this as 1 times 3 to the power n. 3 to the power n itself can be considered as 1 times 3 to the power n. So number 1 is a degree 0 polynomial. So that's in the form of degree 0 polynomial, a polynomial times 3 to the power n. And this number 3 is one of the solution to the characteristic equation. Number 3 is one of the solution to the characteristic equation. So this is case 3. This match case 3. Characteristic polynomial of degree k times r to the power n. This match case 3. The non-recursive part is polynomial of degree k times r to the power n. And here r is a solution of the characteristic equation. Number 3 is a solution to the characteristic equation. So the particular solution must have the form of general polynomial of degree k times r to the power n times n to the power m. M is the multiplicity of this base r. So the particular solution has the form of general polynomial of degree 0. General polynomial of degree 0 is a, is constant a. General polynomial of degree 0 is constant a times 3 to the power n. That's r to the power n. That's r to the power n in the formula. That's r to the power n. Times n to the power m. What's m here? M is the multiplicity of 3. M is the multiplicity of 3. So we have in the characteristic equation we have x minus 3 to the power 1. In the characteristic equation we have x minus 3 to the power 1. So the multiplicity of 3 is 1. Multiplicity of 3 is 1. Here we have x minus 3 to the power 1. That means the multiplicity of 3 is 1. So m must be 1. M is the multiplicity of 3, which is 1. Multiplicity of 3 is 1. So that's the particular solution. Next, we try to plug in a particular solution into the original equation here. Solve for letter A, solve for the constant A. So let's find a sub n minus 1, a sub n minus 2 first. A sub n minus 1 is, I replace each n with n minus 1. Letter A stays the same, 3 to the n minus 1 times n minus 1. Next, we need to find a sub n minus 2. Letter A stays the same, 3 to the n minus 2 times n minus 2. Then plugging here. Left side is a times 3 to the power n times n. Right side, 5 times a times 3 to the power n minus 1 times n minus 1 minus 6 times a times 3 to the n minus 2 times n minus 2 plus 3 to the power n. Then here every term contains 3 to some power here. So I divide by the lowest power of 3. Divide every term by the lowest power of 3. For number 3, lowest power is n minus 2. So first term, divide by 3 raised to n minus 2. I have a times 3 squared here. Let me write it here. Divide every term by 3 to the n minus 2. So first term, if I divide by 3 to the n minus 2, I have 3 squared here. 3 squared times a times n is 9an. Divide by 3 raised to n minus 2, there's a 3 left here. 3 times 4 is 15. I get 15 times n minus 1. 3 to the n minus 2 cancel. We have 6a times n minus 2. Last term cancel. 3 raised to n minus 2. I have 3 squared left. 3 squared is 9. Then simplify the right side. Distribute 15a. I get 15an minus 15a. Distribute 6a. I get 6an plus 12a plus 9. If I combine like terms, I have 9an minus 3a plus 9. Here, 9an on the left side, right side can cancel. 0 equal to negative 3a plus 9. Add 3a to both sides. 3a equal to 9. So a equal to 3. A equal to 3. That means the particular solution. A equal to 3 means particular solution. Here, plug in 3 for a. We have 3 times 3 to the power n times n. Let's 3n times 3 to the power n. It's 3n times 3 to the power n. That's the particular solution. Then we know that the general solution is homogeneous solution plus particular solution. That's homogeneous solution. That's particular solution. The general solution is always homogeneous solution plus particular solution. Next, we use the initial condition. Use the initial condition find C1, C2. This is the general solution. We need to use initial condition to find C1, C2. Initial condition here is A0 equal to negative 1, A1 equal to 3. Plug in. For A0, plug in 0 for each n. 2 raised to power n. 2 raised to power 0 is 1. 1 times C1 is C1. 3 raised to power 0 is 1. 1 times C2 is C2. If I plug in 0 here, 3 times 0 is 0. So the last one is 0. Equal to negative 1. For A sub 1, I substitute 1 for each n. 2 to the power 1 is 2. 2 to the power 1 is 2. I get 2c1. 3 to the power 1 is 3. I get 3c2. If I substitute 1 here, 3 times 1 is 3. 3 times 1 is 3. 3 raised to power 1 is also 3. 3 times 3 is 9. That equal to 3. Simplify both equations. I have C1 plus C2 equal to -1. 2C1 plus C2 equal to -6. Then I can try to eliminate one of the variables first. If I multiply first equation by -2, I have -2C1 minus 2C2 equal to +2. Leave the second equation the same. If I add the equations together, I have 1C2 equal to -4. 1C2 equal to -4. Once I know C2, I can plug in C2 and solve for C1. C1 plus -4 equal to -1. Add 4 to both sides. C1 equal to 3. So the solution is A sub n equal to 3 times 2 to the power n minus 4 times 3 to the power n plus 3n times 3 to the power n. That's the solution to the Recurrence. This is the general solution, and this is the solution to the Recurrence.